Alright, so I just want to go over the answer key for the Kinetics III worksheet. We went over a lot of these in class. We'll go over the logic or the conceptual questions. So 1A, again, this is our data table. It gives us the concentrations of our reactants, and it gives us the initial reaction rates. So the results show that the initial reaction rate increases when the initial concentration of either reactant is increased. Why would increasing the concentration or the partial pressure of a reactant increase the rate at which the reaction proceeds? And the reason for this is that when you increase the concentration, you're going to increase collisions. Right? So when you increase the concentration, you're going to increase collisions, and therefore you're going to increase the rate of the chemical reaction. Okay, so everything is about that collisions and collisions with the proper energy and the proper orientation. So then B asks what environmental factor could be altered in order to increase the initial reaction rate in an experiment. Okay, so the initial concentrations of the reactants are the same, but we want to know what's the environmental factor. And of course, an environmental factor would be an increase in temperature. Okay, so if you increase the temperature, even though the concentrations are the same, you're going to increase the kinetic energy of the particles. Increasing the kinetic energy of the particles means more particles are able to get over that activation barrier and make products. C, we went over in class, the order of the reaction with respect to NO, remember, was second order. The order of the reaction with respect to O2 was, remember, first order, and again we went over that in class. The overall rate law for this reaction would just be rate is equal to K. We don't know what K is, it's just constant. Concentration of NO to the second order and O2 as a first order. So that would be our rate law for this reaction. And then the overall order of the reaction, we just add the exponents, so 2 plus 1 would be 3. Second order plus first order gives us the overall third order reaction. And then the rate constant K, we did do this calculation in class. We end up with 1,700 molar to the minus 2 per second, okay, per molar per second. And then if the same 3 experiments are conducted at a lower temperature, what would happen to the magnitude of the rate constant? And we have to justify our answer. Remember, the justification is always the most important part. So if we decrease temperature, each molecule has less kinetic energy, which means we're going to have fewer collisions to produce enough energy to get over that activation energy barrier. So at lower temperatures, each molecule has less kinetic energy, which makes it more difficult to get over the activation energy barrier, which means you're going to have an overall rate that is lower than the initial rate stated up here, and which means your rate constant K must have it must be because the rate constant K is a smaller value. Okay, your initial rate is going to decrease. Your rate constant K must decrease because your concentrations of reactants are the same. Okay, so that's our justification here. If we go to question 2, not all collisions between reactants result in the formation of products, and we have to explain. So for most reactions, most collisions don't actually cause a chemical reaction because you need to have the orientation and sufficient energy. And remember, orientation is completely random. Okay? Orientation is completely random. The next question is number 3. Some reactions are considered to be thermodynamically favored at low temperatures, but will not proceed at an actual measurable rate, okay, or form any measurable quantity of products. Why would this be? So remember, thermodynamic favorability is different than kinetic favorability. So whenever we have reactions under these conditions, so they are thermodynamically favored, but they're at low temperatures. Remember, temperature is equal to your kinetic energy. So even though they may be favorable, they're under what we call kinetic control. Okay, we call this kinetic control. And what that means is they don't have sufficient energy, again, to make it over that activation barrier. Okay. And then 3b says, will the addition of a catalyst alter the value of delta G for the reaction? We know that a catalyst changes the activation energy. We know that the equation for delta G is delta H minus T delta S, which has nothing to do with activation energy, which means that the addition of a catalyst will not change the delta G value for a reaction. Okay, and then 4, we want to know the difference between the activation energy and the delta E. So that goes to our thermodynamic graphs. Remember, your activation energy is the distance between the reactants and the top of this hump here. That's your activation energy. The energy required to minimum amount of energy required for a reaction to occur, where this delta E is the difference in final potential energy, right? Potential energy from reactants to the products. So it's the difference in that stored energy, the energy that's overall stored in the chemical bonds of your reactants and your products. All right, if we move on to question number 5. Question 5 says the energy profile diagram below is plotted for a second order elementary reaction. A plus BC is in equilibrium with AB plus C. At low temperatures, you have a relatively small fraction of collisions reacting and resulting in the formation of products. Describe the interactions between reactants that collide with an orientation that would produce products but failed to do so. Okay, so what this is asking us to do is describe those intermediate steps. Describe the particles in those intermediate phases. So describe the interactions between reactants that collide with the orientation that should produce products but didn't do so. So we know that the orientation was correct, which means the kinetic or the total energy was not sufficient. Okay, so if the two species collide with the correct orientation, okay, good orientation means the energy is not sufficient. Okay, correct orientation means the energy is not sufficient, so the two molecules will bond together temporarily, but they will not produce products. So the temporary bonds will lose potential energy, and they'll come back down back to your initial reactants. Okay, so what our reaction ends up, it's A plus BC. It comes together to make these temporary bonds, but then it doesn't have sufficient energy to make it over the activation energy barrier, which means you go back from A, B, C temporary bonds back to A plus BC, which was your initial reactants. Okay, and then B for this one says that at high temperatures, you have a large fraction of collisions result in the formation of products. So now we want to describe the interactions, same thing we did up here. Describe the interactions from the moment of the collision to the formation of your products. So we know that when two molecules collide, the kinetic energy from their motion is converted into potential energy. The potential energy is what creates these temporary bonds. And then in this case, so we end up here, right? We have collisions, we form these temporary bonds, and then in this case we have high temperatures, which means we have sufficient kinetic energy to get over the activation energy barrier. So instead of going back to reactants, we can actually make it all the way to our products AB plus C. So our bond here is the AB bond, and C as a lone product. Okay. We know here that our potential energy, so we see that our difference, we see that our difference in energy, our reactants, are slightly higher in energy than our products. Okay, so we know that when this happens, the potential energy of our components begins to drop. And you form this AB bond with C as your individual product. Okay, so that's what I mean by describe the interaction. So it's the formation of these temporary bonds. Okay, it's the formation of those temporary bonds. And we go over to 6. Question 6 we did do in class, but we may as well briefly mention it again. So the graph below is to find the activation energy for a chemical reaction. We see that our x-axis is 1 over the temperature, which means, and we're solving for, label the y-axis and then calculate the activation energy. Because it's activation energy, we know that we have to use our Arrhenius equation, which is ln of K is equal to negative activation energy over R times 1 over T plus the natural log of A. Okay, so y equals mx plus b. So which means our labeling the y-axis is natural log of K, and then we have to calculate the activation energy, which we did in class. The key here is to remember that your temperature axis label is not actually 3.3, but it's 3.3 times 0.001. So when we calculate our slope, we have to take this into account. The other thing to keep in mind is whenever you're given a question like this, you always want to pick points that are very close to an actual intersection of the two lines. That way your data is guaranteed to be as best as it can be, okay, or as close to the correct answer as possible if you pick points that are actually intersecting on intersecting lines in the graph. All right, question 7. Pardon the coffee spills. Question 7 says a chemical reaction takes place in a beaker that you're holding. While the reaction's taking place, your hand feels cold. We did go over this one in class. Remember, if it feels cold, that means it's absorbing heat, which makes it an endothermic reaction. So when we make our energy diagram, it's absorbing energy, which means that our reactants are going to have lower energy than our products. Okay, and the important thing to remember here is your labels potential energy is increasing, and this is your reaction progress as you go across this away. Okay. Question number 8, what's the difference between a reaction intermediate and a catalyst? Okay, a reaction intermediate we know is a product of elementary step 1, and it's used in elementary step number 2 of the reaction. Okay, so an intermediate is actually not present. Oops, let me see. An intermediate is actually not present in the final overall chemical equation, and then a catalyst is a reactant in elementary step number 1 and is a product in elementary step number 2. Okay, this is elementary steps, remember, from your reaction mechanisms. We know that a catalyst lowers the activation energy, whereas an intermediate does no such thing. And we know that it's not produced or consumed by the reaction. So where it starts is where it ends. All right, question number 9. We went over this one in class, so I'm not going to cover it here, but I will give you, well, briefly, and then question 10 is exactly the same. 11 is a little different because you have equilibrium steps, but we'll get to that in just a minute. So question number 9, we have our two-step mechanism that give us the slow step. So the overall reaction, we just have to cancel out our intermediate products. So we have F as a product, or as a reactant here, as a product here, and NO2, so we have F2 plus 1, 2, 2 NO2 reacts to make 1, 2, NO2 F. Oh, 2. So that's our overall reaction. We know that F is an intermediate because it's present over here as a product in step 1, and it's used up as a reactant in step 2. The rate law for each elementary step, remember we use the coefficient concentration, or coefficient times the chemical plus coefficient CC plus D, and we can use those to write our rate law. Rate is equal to K A to the power of B, whatever our coefficient is, B to whatever that coefficient is. And remember, this is only okay for the elementary steps, for these little steps 1 and step 2 in our reaction mechanism. So this is how we can solve the rate law for the elementary steps. And then the rate law for the overall reaction is going to be equal to the rate law from the slow step of the reaction. Okay, so our rate law for the overall reaction ends up being rate is equal to K times the concentration of NO2 to the first order, concentration of F2 to the first order. And so that's our overall reaction, because the rate of the overall reaction is equal to the slow step. Okay, question 10 is much the same. So question 10, we have to cancel out our intermediates. So we have chlorine as a product here, chlorine as a reactant here. We have NO2Cl, NO2Cl, so we have 2 of these on the reactant side. Products NO2, NO2, and Cl2. So our overall reaction is 2 NO2Cl. Breaks down, decomposes into 2 NO2 plus Cl2. Okay, that's the overall reaction. It asks, is chlorine a catalyst or an intermediate? Again, it's an intermediate because it's a product here, and it's used up as a reactant here. Okay, and again, chlorine, this is the chlorine radical, right? It's not diatomic, so this makes this a chlorine radical. And then the rate law for each elementary step. So the rate law for this slow step here is going to be rate is equal to K concentration of NO2Cl to the first power, and the rate for our fast step is going to be equal to K, and we can call this K1 and this K2, just so we can distinguish K1 and K2. And then here it's going to be the concentration of NO2Cl times our chlorine radical. And because the rate law for the overall reaction is equal to the slow step, this is also the rate for the overall reaction. 11 is a little bit more complex because we have an equilibrium. It's a little bit more complicated because we have an equilibrium. So we have our two-step mechanism where we have 2NO is in equilibrium with N2O2, and our second step is N2O2 gas plus bromine reacts to form 2NOBr. This is our slow step, which means this is our rate limiting step. Okay, that's a slow step, that's our rate limiting step. So the overall reaction, again, all we have to do is go through, cross out our intermediates, make sure that nothing is on the product side in one and reactant side in another. And our overall reaction is 2NO plus Br2 makes 2NO Br. Oops. All right, is N2O2 a catalyst or an intermediate? Again, we're dealing with an intermediate. Product in step 1, reactant, and completely used up in step 2. Okay, it's produced and consumed by the reaction. The rate law, now it's just asking for the rate law of the overall reaction, so we don't even have to do the rate law for the equilibrium. We can just say rate law for the overall reaction. We know that our slow step rate is equal to K, concentration of N2O2, concentration of Br2, but because our overall reaction contains an intermediate, we actually do have to do the fast equilibrium as well. That way we can get our final overall reaction rate law in terms of our true reaction, reactants, and products. Right? Our true chemical equation reactants and products. So, if we look at our equilibrium, our rate, so we're going to have K1 is our forward reaction, K minus 1 is our reverse reaction. So our rate is equal to K1 times the concentration of NO squared. And then we also have, that's equal to, because they're in equilibrium, K minus 1 is the concentration of N2O2 to the first power. Okay, so now we can just divide by K minus 1, divide by K minus 1, and plug this in here. When we do that, so this is our K2, obviously. When we plug this in, we get K2, K1, K minus 1, concentration of NO squared, concentration of Br gets brought down here. Okay, so this term here is this term here. And then if we just combine our K values, we'll call all of this together K3. So our rate is equal to K3, concentration of NO squared, times the concentration of Br. Okay, and then it wants the order of the reaction with respect to NO according to the above mechanism. The rate law with respect to NO according to the above mechanism is the second power. Okay, and we know this because it's raised to the power of 2. We have this coefficient of 2. We use this rule up here to determine the rate law of the elementary steps. So it's second order with respect to NO. Okay, then we'll go on to question 12. So the rate law for the overall reaction, the rate is equal to K times the concentration of NO times the concentration of Cl2. It gives you the proposed steps for the reaction and the proposed and the final overall reaction. So it's asking, is NoCl2 a catalyst or an intermediate? If we look at NoCl2, we see that it's a product in the first step, used up in the second step, which again makes it an intermediate. Okay, which step occurs the fastest? Okay, which step occurs the fastest? So we have to know this, we have to look at our rate law. Our rate law is always going to be equal to the slow step. So NO and Cl2, NO and Cl2, that makes this our slow step, which means that this step is the fastest. And then which step determines the overall rate of the reaction? That would be this one, and we know this because the rate law of the overall reaction is equal to K, concentration of NO, concentration of Cl2. This is also the rate law for step 1, and that means that step 1 is the slow step, which determines the rate of the overall reaction. Okay, we go on to question 13. There's a two-step reaction outlined below. Okay, so they tell you the slow step, they give you the fast step, and they outline the reactants and products that we have to find the overall reaction, which means the first thing we have to do is identify what's the same on the reactant side as is on the product side. We can do this by just writing out H2O2 I minus H2O2 plus IO minus products H2O plus IO minus plus H2O plus O2 plus I minus. Okay. On the reactant side, on the product side. On the reactant side, on the product side. So our overall reaction is what's left over, right? Just like our net ionic equations, this is done the same way. So we have 2 H2O2 reacts to make 2 H2O and 1 O2. We don't need that coefficient in there. I minus, is it a catalyst or an intermediate? We look over here at I minus, it's in the reactants in step 1, it's in the products in step 2, which makes I minus a catalyst. And IO minus is in the products of step 1, it's in the reactants of step 2, which makes this an intermediate. What is the rate law for each elementary step? We can look and we see that these are both not equilibrium reactions, so we give them K1 and K2. The rate law for the first one is going to be rate, we'll do it up here. So the rate is equal to K, concentration H2O2 times the concentration of I minus. minus. And rate for the second reaction, oops, this one's the first reaction is K1, we name this one K2, is the concentration of H2O2 and the concentration of our intermediate IO minus. Okay, so the rate for each of the elementary steps, this and this, and then the overall rate of the reaction is equal to the slow step, which means this is the rate for the overall reaction. Okay, we'll go on to question 14. Question 14, the graph below shows a plot of ln A versus time for a first order uncatalyzed, ln of A versus time for a first order uncatalyzed process. The rate law for the overall reaction is rate is equal to K times the concentration of A. We have to draw a line that would approximate the process in the presence of a catalyst. Okay, we know that a catalyst is going to speed up the reaction. Okay, so it doesn't really necessarily change our concentrations. It's going to affect our time. And our concentration in presence of a catalyst is going to decrease faster as time progresses, which means our line should be something, like this. Okay, it doesn't give us any specific information on the catalyst. It doesn't tell us exactly how much it decreases. So as long as your line is something like this, that's what we're looking for. Okay, your concentration is going to decrease in the presence, faster in the presence of a catalyst. So we want this more dramatic slope. Question 15, this is a reaction energy profile diagram outlines an uncatalyzed process. Approximate the plot for this process in the presence of a catalyst. Again, we know that a catalyst lowers the activation energy. We know that the activation energy is the distance between your reactants and this line up here, which means your energy for your reactants is going to be the same. You're going to take a different, lower activation energy, and you're going to have those products be the same as well. Okay, so all you're doing is changing EA, the activation energy. And this would be your catalyzed process. Okay, label the activation energy. Did that. Label delta E. We know that delta E is the distance between the reactants and the products, so the delta E is this small disparity in here. What else? Explain why the presence of a catalyst increases the reaction rate. The explanation for this one is it provides an alternate mechanism for the reaction that has a lower activation energy. Okay, when the minimum collision energy required to trigger a chemical reaction is lower, you have a higher percentage of collision between reactants that'll end up in chemical reactions. Okay, so if you have more collisions per period of time, end up resulting in a product, the reaction rate is then higher. Okay, so catalyst lowers your activation energy, which means more reactants collide with sufficient energy to produce your products. Okay, which ends up being more product per unit time, which explains the increased reaction rate. Question D, so 15D is the process endothermic or exothermic. To know this, we have to look at where we started versus where we ended up. Our reactants are lower in energy than our products, which means the energy, albeit a little bit of energy, was absorbed, which makes this process endothermic. Okay, delta E reactants is lower than products, which means energy is absorbed, which makes it an endothermic process. 16 says, although the presence of a catalyst speeds up the rate of a reaction, the value for the equilibrium constant KEQ remains the same. We haven't talked about equilibrium just yet, but it's a good little preview for the next lesson. Okay, so to answer this question, again, catalyst lowers the activation energy for both the forward and the reverse reaction. So whenever we're dealing with EQ, equilibrium, we have a forward reaction and we have the reverse reaction. So catalyst lowers the activation energy for both forward and reverse processes. So this increases the rate of the forward reaction and of the reverse reaction. So the presence of the catalyst will have the same system, or will cause the system to move towards equilibrium faster, but the equilibrium position, which is KEQ, where it ends up being the same. Okay, so again, catalyst changes the rate, but not the final product. Okay, just as we saw up here, it changes the rate of the reaction, how fast you get there, but it doesn't change anything about the final products. Question 17, if the activation energy of the forward reaction is the same as that of the reverse reaction in an equilibrium system, what can be said about the value of delta H? Okay, so your activation energy for the forward reaction is the same as that of the reverse reaction. What do we know about delta H? If your activation energy for the forward and the reverse are the same in an equilibrium system, your delta E is going to be 0. Okay, if you're because here you can clearly see that your activation energy is going to be slightly different for the forward and the reverse. If the activation energy is the same as the reverse, then that means your delta E is equal to 0, which means your change in enthalpy from reactants to products is also going to be 0. Okay, so if the forward activation energy of the forward is the same as that of the reverse, that looks like a graph where your products and your reactants have the same energy. And what that means is your delta E is 0, which means your enthalpy change is 0. And finally, question 18. The reaction is found to be second order for A, 0 order for B. The mechanism proposed for this reaction, 2A results in CE, BE results in A plus D, where step 1 is your slow step, step 2 is your fast step. What's the rate law for this reaction? So it's looking for the overall rate law. So we have to go to our slow step. Neither of these is equilibrium, which means that our rate is going to be equal to K, concentration of A, and these are intermediates, which means we can just use that coefficient as our order. And these are both, sorry, not intermediate, elementary steps. These are both elementary steps, which means we can use the coefficient as the exponent. Okay, and then we have to give 2 reasons why the above mechanism is possible. So this mechanism is possible because your reactants, so when the 2 reactants are added together, when you add this plus this, E cancels out. You end up with 2A plus B. One of our A is produced here, which means we end up with A. So our overall reaction, A plus B makes C plus D, which matches our proposed reaction, our original reaction. And then the slow step is consistent with the rate law. Okay, the slow step is consistent with the rate law since B is 0 order and second order for A is here. So this is, our rate law is consistent with our proposed, or our equation and our known order of the reactions. That's it. If you have any questions on it, we can go over it in class. We'll do a review tomorrow, and then we'll have a test on Tuesday.